Good morning. We'll start session 3 on chapter circles. So first we will finish all the theorems with respect to the chord properties and angle properties of the circle, and then we will start with the exercise. So theorem, I'll just write this as theorem 1. So the first theorem is the perpendicular which is drawn from the center to the circle bisect the chord, and we have already proved that in our previous classes. So that's the theorem. Theorem says that the perpendicular from the center of circle to a chord bisects the chord. Okay, draw a circle, and this should be a neat figure, not a rough figure. A circle what you draw should be with your compass neatly. So always O is the center of circle. We'll consider that AB is a chord and OP is perpendicular to AB. Given O is the, and all these theorems what we are proving are proved by congruency. O is the center of circle. This is how we write the circle. The second point is AB is the chord, and the third point what we know is here OP perpendicular to AB. Now what we have to prove? The perpendicular drawn from center of the circle to the chord bisects the chord. We have to prove that AP is equal to BP. Construction. We need to prove the sides are equal. That is by congruency what we can prove. Construction. Join OA and OB. So join these two sides. Prove in triangle AOP and triangle BOP. So first of all, can I tell that angle OPA is equal to OPB, that is equal to 90. That's because OP is perpendicular to AB. First one. Next one, OP is equal to OP. Reason, common side. So this is equal. OA is equal to OB. Why OA is equal to OB? These are nothing but common radii. Oh no, sorry. Radii, not common radii. Radii of same circle. But now this side is equal. So we have two different sides and an angle. But if you see that it is a 90 degree, that means a side opposite to 90 degree is nothing but an hypotenuse. We saw that one 90 degree hypotenuse and a side is equal. Therefore, a triangle AOP is equal and congruent to triangle BOP by RHS congruence rule. So, from RHS congruence rule, can we tell that the corresponding sides are equal? AP is equal to BP. Reason, CPCT. Hence proved. AP is equal to BP. The perpendicular drawn from center to chord bisects the chord. We have a similar one for the converse now. Now what does the converse tell here? So we will give the heading here as, I only rub this much of part, and we'll make some adjustments in this one only, which you have to repeat it once again. Okay, I'll rub what I have drawn. So it is converse of theorem 1. Converse of theorem 1 tells us that the line drawn through the center of a circle to bisect Let a chord is perpendicular to the chord. That means if you draw any line from center to the chord, that line will bisect. That means that line is perpendicular, what we have to prove here. Okay, so just we will reverse this part. This part will not come. Rest everything will remain the same thing. Now let's see. Okay. O is the center of circle, AB is the chord, and they have also given that AP is equal to BP. Right? What we have to prove? We have to prove that OP is perpendicular to AB. This way what we have to prove. 90 degree what we have to prove here. Construction same thing. So in triangle AOP and BOP, two triangles we have chosen. Now we have a common side. Then we have this side is equal to this side. So let's write down that OP is equal to OP common side. OA is equal to OB radii of the same circle. AP is equal to BP given. Therefore, triangle AOP is equal and congruent to triangle BOP by triple S congruence rule. Okay. From this, I can tell that angle OPA is equal to angle OPB CPCT. But 90 degree it is not given. Now next part, what do we do now? Since it's a linear pair, we know that angle OPA plus angle OPB is equal to 180, linear pair. Okay, but OPA and OPB are equal to each other. Can I write here 2 times of OPA is equal to 180. Angle OPA is equal to angle OPB. Therefore, angle OPA is equal to 90. Right? 2 goes to divide over there. This implies angle OPA is equal to angle OPB is also equal to 90. Therefore, OP perpendicular to A. Hence proved. Right? This is the converse of the theorem. Theorems are quite simple. It is like as good as proving congruency for the given part. So this is about the one chord property. So what's the next chord property what we have? Equal chords of the circle are equidistant from center. Let us start with that, and we have a converse of that theorem also. So theorem 2. These theorems are again asked in the exercise 1 or 2. At that point of time, we need not repeat it once again. So, theorem 2, it tells that equal chords of a circle are equidistant from the center. O is the center of circle. Let me consider this is one chord. Let me consider this is one chord. AB and CD are the two equal chords given. O is the center of circle. AB and CD are the two equal chords. Therefore, AB is equal to CD. Okay, they are equidistant from center. What we have to do? They are equidistant from center is let us consider one point here. It's not a construction, but we can say draw OX perpendicular to AB and OY perpendicular to CD. OX and OY perpendicular to CD. right? What we have to prove now? To prove OX is equal to OY, equidistant from center. Construction. Join one pair, whichever you want. Join OB and OD. I will choose, or you can say OA and OC also. So join these two sides. Choose those triangles. They are perpendicular. Proof. In triangle BOX and triangle DOY. Okay. First of all, 90 degree, we will write that angle OYD. Okay, BOX we have chosen. No, first we'll write that angle OXB or angle OXB is equal to angle OYD is equal to 90. That's because OX perpendicular to AB and OY perpendicular to CD. 90 degrees over. Then can I tell OB is equal to OD? OB is equal to OD. They are hypotenuse. We know that. Also they are radii of the same circle. Radii of same circle. Then CD is equal to AB, right? So half of CD is also equal to half of AB. So what is half of CD? BX is equal to DY. Reason I will tell, half of AB is also equal to half of CD. Chords are equal, halves of equals are equal. So we have hypotenuse which is equal, these two which are equal, and a 90 degree. 90 degree hypotenuse are assigned. Triangle BOX is equal and congruent to triangle DOY by RHS congruence rule. Okay, so from this can I tell now OX is equal to OY CPCT. Equal chords are equidistant from center. The converse tells that the chords which are equidistant from center are equal. If I tell that OX and this are equidistant from center, then the chords are equal, right? That's the converse. We need not prove that, but usually it can be asked also. We will just state the converse, but we are not proving the converse here. Okay? Is this very clear? Even if it is asked to prove, children, I think it should be very easy because all the theorems what we have on circles chapter are at least the chord properties what we study are based on congruency. So converse we will only state, but we will not prove it. Converse of theorem 2. Chords equidistant from the center of circle are equal. Okay, we can just prove it. Now let's come to the angle properties what we have studied. Now this angle properties when we talk about, it's about angle subtended by a chord. That is central angle is twice the inscribed angle. That theorem we are going to prove now. A very important theorem. I will just mention it as a theorem 3 here. Theorem 3. Theorem 3 tells us that the angle subtended by an arc at the center is double the angle subtended by it at any point on the remaining part of the circle. Okay, so as usual we can say that O is the center of circle. O is the center of circle, as usually what we tell. The angle subtended by an arc at the center. So let us have an angle subtended by an arc at the center. So we'll name that as, if I consider this, AB is an arc and AOB is an angle subtended by the arc at a center, is double the angle subtended by it on the point of any remaining part of the circle. Okay, so given, first always point should be O is the center of circle. That's the first point. Then angle AOB is the central angle subtended by arc AB, and angle ACB is the inscribed angle subtended by the same arc. Subtended by the same arc. This is the given. Always the first given should be O is center of circle, like how we prescribed in triangle. ABC is a triangle. So here O is center of circle. Now what we have to prove? I'm going to rub these things what we have to prove and all everything, and directly start from here. Theorem is a bit lengthy here. To prove angle AOB is twice angle ACB. Central angle is twice the inscribed angle what we have to prove. Construction. Join CO and produce it to E. Join CO, okay, and produce it to E. Don't touch the circumference here. Okay, this much is done. So let me rub the whole given part. I'll only write what we have to prove. Angle AOB is twice angle ACB. This is my proving part. Very clear on what we have done till here? Yes. I'll just erase this and start the proof from here. A very important theorem usually asked from this chapter. Okay, proof. Let me consider the first part of a triangle. In triangle AOC. Okay, so in triangle AOC, can I tell OC is equal to OA? Why? Because radii of same circle, right? OC is equal to OA, radii of same circle. If OC, which angle will come? This angle. And if it is OA, this angle will come. With respect to OC, can I tell that angle OAC is equal to angle OCA? Angles opposite to equal sides are equal. Angles opposite to equal sides are equal. Keep this as this. Then, if I consider children, this is the exterior angle. We know that angle AOE, if it is an exterior angle, just look, which are the two opposite interior? This plus this, right? Angle AOE is equal to angle OAC plus angle OCA because exterior angle theorem. Angle AOE, but these two are equal, right? Can I write this as twice angle OCA? See, I can even write twice OAC, but I will use this because this is the part of the inscribed angle. That's why. Reason you can write here, angle OAC is equal to angle OCA, right? Equation 1. Keep this as it is. Similarly, second set of triangle, what we have in triangle BOC. So in triangle BOC, can I tell OB is equal to OC? Same thing what we have done, I am going to repeat that for the next set of triangle here. Reason, radii of same circle. Since it's a radii of the same circle, if it is an OB, so it will be this angle, and if it is an OC, it's going to be this angle. So angle OCB is equal to angle OBC. Reason, angles opposite to equal sides are equal. Keep this answers. Done. Again, we know that angle BOE is equal to, so angle BOE, this angle is equal to sum of the two opposite interior angles, same as the previously how we have written, angle OCB plus angle OBC. Reason, exterior angle theorem. But I will write angle BOE as twice angle OCB. I will choose the upper part because it is a part of an inscribed angle. Equation 2, because angle OCB is equal to angle OBC. Add equations 1 and 2. Add 1 and 2. Angle AOE plus angle BOE is equal to, 2 common shall I take? Angle OCA plus angle OCB. Angle AOE plus BOE. AOE plus BOE is together angle AOB. Twice as it is. Angle OCA and angle OCB is together angle ACB. Twice angle ACB. Central angle is twice the inscribed angle. A very simple theorem, but you have to just follow this. Actually, theorem is very simple. You are not using congruency here. We are using what we have learned in lines and angles exterior angle theorem, and in triangles chapter, the angles opposite to equal side, that property we are using, and proving that an angle subtended at the center of the circle by an arc is twice the angle subtended by any point on the circumference subtended by the same arc, which is nothing but, in shortcut we say, central angle is always twice the inscribed angle, and we have also proved it by drawing some set of constructions of central angle with respect to inscribed angle. A last theorem where we have learned also about a cyclic quadrilateral. Opposite angles of a cyclic quadrilateral are supplementary. The theorem is actually not mentioned in the book, but I still want you all to know how actually it is. So, theorem 4. Opposite angles in a cyclic quadrilateral are supplementary. Okay, so let's have a circle again. We will consider O is the center of circle. Where ABCD is a cyclic quadrilateral. Given O is the center of circle, ABCD is the cyclic quadrilateral. Okay, what we have to prove? Which angle side you have to prove? You have to decide first. Any one where angle B plus angle D is equal to 180, or angle A plus angle C is equal to 180. One pair you can prove. That's all. Construction. Let us join whichever side, opposite sides you want, that particular diagonal part, what we can join here. Join OA and OC. Okay, keep this as it is. Then, proof. Okay, now suppose if I consider this is my central angle, then this will be my inscribed angle, right? I will write it. Angle AOC is twice angle ABC. Okay, angle AOC is twice angle ABC. Central angle is twice the inscribed angle. There are two things together. I will write that. Angle AOC, this side I have taken is twice of this. If I consider this side of AOC, I will write that as reflex AOC. Actually, this is looking reflex than that. Okay. Reflex AOC is twice angle ADC. Together we can have the same reason. Okay, we'll do one thing. Wait, we will shift the center a little bit here and make it look like a reflex angle. Otherwise, what we write and what we draw here, it looks different. Let us make it look like that. Okay. Now, yes, this is O. Now will AOC look as this will look as a central angle, but when I talk about this AOC, that will look like a reflex. See, this central angle is twice of this central angle is twice of this, but that is reflex AOC is twice of ADC. Central angle is twice the inscribed angle. Keep it as it is. Next part. Angle AOC plus reflex angle AOC is equal to 360. Complete angle. Right? What is AOC? Twice ABC. What is reflex ABC? Reflex AOC twice angle ADC is equal to 360. Take 2 common. ABC plus ADC is equal to 360. Now, what is this ABC? 2 we can shift that side. ABC plus ADC. 2 goes here, 180. Over. Very simple theorem what we have. This is opposite angles in a cyclic quadrilateral are supplementary. So with this we complete all the theorems of the chapter circles. Now we are only left with some writers as well as some numericals on this, which we will be doing it in the next session. Along with the numericals, we have also some theorems repeated what they have asked, but we will just skip them as we have already completed all the theorems in one session.